Sylow, I think. Yeah. So what we've had so far is theorem 15.1, which is attributed to Cauchy, that says if prime P divides the size of your G, then G has a subgroup of prime P. Or another way of saying that, it has elements of order P. Okay? The subgroup of order P has to be cyclic, generated by any of its non-identity elements. Okay? This is made better, generalized in the first Sylow theorem, to the exact same statement, except this time we're talking about a power of a prime. Any power of the prime, as long as it divides the size of the prime. In order for there to be a chance of there existing a subgroup of this order, then this number has to be a divisor of the size of the group. It's just from Gron's theorem. The Sylow theorem says something positive and descriptive. It says there is a subgroup of this size. And you certainly can't say that for every divisor of the size of G, because when you've got your, well, we've seen counterexamples of groups that don't have subgroups of certain orders for certain divisors. So once we know this, our focus then goes to the biggest such groups. Okay? And these are what are called the Sylow P subgroup. Now, I alluded to this in the tutorial last week, but there are two competing or two equivalent definitions which are subtly different. Okay? The one that Judson presents in the book, and there's a slight, myself and Jan talked about this, or Jan, spots a little particular, I think I spotted it as well the previous years, but the chapter needs a little bit of a rewrite to straighten this out, or needs some additions. Okay, because one way of defining this is a P subgroup H of G, i.e., that's saying the order of H. So a P subgroup, well, two things about that. So a P group is one where you only see elements, the elements in the group, they all have orders some power of P. Okay, so you only see elements of order a power of P. And we've also proven that, well, that combined with Cauchy implies such a subgroup like that, it's the order of the subgroup itself must be a power of P. So let's say P to the L for sub L.
Why the order of subgroup must be the power of P?
Well, that's a consequence of Cauchy's theorem, because if it wasn't a power of P, in other words, if there was another prime that divided the side of H, then Cauchy's theorem would tell you there are elements of order Q in H. But the original definition of a P subgroup was one where the elements only had all the elements had order some power of P. Yeah. So it's a combination of that definition of Cauchy's theorem means that the order of such a group must itself be a power of P. Now, okay, this definition isn't finished. So a Sylow P subgroup is a P subgroup of H that is maximal. What does maximal mean? Well, it means biggest in some sense. It means biggest in terms of the sense of set inclusion. So, i.e., H is itself contained in no other P subgroup of G. Okay. So according to this version of the definition, a Sylow P subgroup is the biggest P subgroup we can find in this sense. The sense that it is contained in no other such P subgroup. Or, the second version of it, if the order of G is P to the R times N, and P does not divide N, so i.e., P to the R is the biggest power of P within G. And a Sylow P subgroup of G is a subgroup H of this order. The order of H equal to this biggest possible power of P. Okay, you can agree that the two definitions are different. They are equivalent, and we'll prove the equivalence of them now. In some senses, I think the first version is perhaps a more elegant definition. It perhaps speaks to, maybe this notion of being maximal, being a subgroup of a certain type, and not strictly contained in any other subgroup of that type. That's in some sense identifying the kind of crucial point. The second version of the definition is a little bit more explicit and singles out the exact size of these subgroups directly. It says specifically what size they are. They are size P to the R, where R is the biggest power of P within the size of G. Whereas the thing that at first glance, what definition 1 leaves open is that there could be Sylow P subgroups of different sizes. Okay. So some Sylow P subgroups might have size P to the R, the largest power of P within the size of G, whereas other ones might have a slightly smaller size. There might be a lower power of P, smaller power of P. Definition 1 doesn't explicitly rule that out. Now, the two definitions are equivalent, which we'll be able to argue for now. So, whichever one you adopt, you can then use the statement of the other one as a kind of consequence of the definition. But in Judson's book, he declares this definition, but then in his arguments, he uses this fact that the Sylow P subgroups have this size, this biggest possible power of P size. But he doesn't justify it. So that's a slight gap in the book. There's one little advantage to definition 1 is definition 1 could apply, and I think the concept does apply, to infinite groups. Obviously, you can't talk like this if the group G is infinite, yeah, because if the size of the group is infinite, it doesn't have a prime factorization. And it doesn't mean anything to say that this power of P divides the size of G, if the size of G is infinite. Whereas this definition doesn't explicitly insist that G is infinite. It just talks about a subgroup of a certain type of G, namely a P subgroup. All its elements have finite order some power of P, and it says it's maximal. It's not contained in any bigger one. So definition 1 could be applied to infinite groups. You'd have to prove that such things exist, although there's always, such things do exist trivially because the trivial subgroup, size 1, well, no, you don't know for sure that they exist because there could be an infinite chain, chain of subgroups of bigger and bigger and bigger size that are all P subgroups, I guess. But at least definition 1 potentially could be applied to infinite groups. Any questions just about the two definitions? Everybody see that they are different. So the first one doesn't make explicit reference to just what this size of H is. I mean, I know it mentions it, but it doesn't say anything about, is this the full power of P within the size of G or not? And it certainly doesn't declare that all the C-log P subgroups are the same size. Whereas this definition zeroes in and it declares what size they have. And by implication, then they all have the same size, all the C-log P subgroups. And this size is explicitly given as the biggest power of P that divides the size of G. Okay.
They're the same, aren't they?
Well, we need to prove they're the same. Certainly, definition 2 implies definition 1. That's the first thing. So these are equivalent. So in order, strictly speaking, in order to make sense of the rest of the book, we either have to explicitly adopt this second definition instead, or prove that the first one implies the second. So that's what we'll do this. Definition 2 implies 1. This is immediate, I think. Yes, this is immediate. For a subgroup of size, a subgroup H, of size P to the R, cannot be contained in a strictly bigger P subgroup of G. Why not? Why is that true? Is that obvious? Does that need further clarification? So why, if how will you convince us?
Because it's not dividing M.
Yeah.
Because P does not divide M. Then.
P does not divide M. So this supposedly bigger P subgroup of G, how big would it be? Well, its size would have to be some bigger power of P. But that would violate Lagrange's theorem, wouldn't it? Because the size of a subgroup has to divide the size of G. And if the size of H is already this biggest power of P within the size of G, then you can't have a bigger P subgroup containing H, strictly bigger. Because its size would have to be a higher power of P, bigger power of P, but a bigger power of P can't divide the size of G. Because this has all the factors of P in it.
Because P doesn't divide M.
Exactly, yeah. P doesn't divide M. So this is a subgroup H cannot be contained in a strictly bigger P subgroup of G, as this would have size, this would have order strictly bigger than P to the R. Well, this would have order P to the K for some K strictly bigger than R, and this would violate Lagrange's theorem. Okay, so definition 2 implies definition 1. Okay. So subgroup H of G, which has this biggest possible size, because for a P subgroup, it is maximal. It's not contained in any other P subgroup. Okay. For 1 implies 2, this needs more work.
And why did you say that violates Lagrange's theorem?
It's a how big, yeah. So it's like a quick proof by contradiction. Suppose there is a bigger P subgroup that contains this H. If it's bigger, it has to have size bigger than H. If it's a P subgroup, its size must be some power of P. So this subgroup would have size P to the K. K is strictly bigger than R. But that number, P to the K, cannot divide the size of G. Because there's only R factors of P within the size of G. You can't take any more. There aren't any more. Okay, so such a bigger P subgroup couldn't exist because it breaks Lagrange. Okay. Okay. Now, for 1 implies 2, this needs a proof. So let Q be a maximal P subgroup. G. So it's a P subgroup, so the order of Q is P to the L, some L. And suppose further that the size of G is P to the Rm, with P not divided. So clearly, L has to be less than or equal to R. What we're going to prove now, we're going to prove that L equals R. L has to equal R. Okay. This maximal, there are certainly subgroups. There's no problem with having a subgroup of G of size P to the L. That's going to exist for sure. But it won't be a maximal one. It'll have to be sitting inside a larger P subgroup. But assuming it's maximal, it implies, it forces the size of the subgroup to actually be the full power of P. And to further illustrate the kind of power of the idea, the concept, this proof uses group actions. Okay. So we'll consider, so let P be a subgroup of G of order P to the R. So we know that exists from the first Sylow theorem. Okay. P exists by the first Sylow theorem. Yeah. Let C equal the set of left cosets of capital P and G. Yeah. How many left cosets will there be? How many left cosets of P and G?
Oh.
Yeah.
One.
So that
because it has to multiply the
it's the quotient.
multiplication should be the same as the order of G.
Yeah. So the size of the subgroup, remember all the left cosets have the same number of elements. This was how we proved Lagrange's theorem. So the number of left cosets is just the quotient of the size of G divided by the size of P. So it's this number n. So if I've got a P itself and then G1, G2, so this counting, is indexing is going to go up to G n minus 1. Okay. So there's n multiples. And we've identified a set of representatives for the identity. You could consider the identity as the representative here, G1, G2 to Gn minus 1. Now, the group action is, consider the action of Q on C by left multiplication. Multiplication on the left. So the action is that if, so for Q, for an element little q within the subgroup Q, and the action of Q on a coset GIP, well, is just the set theoretic, just the product. Q times this. Okay, the set of all elements from the coset, all of them multiplied on the left by Q. Now we do our counting this. So in the remember in the language of group actions, we had a group G acting on a set X. So the Q is the group G here, and the set X is this set C of cosets. And remember this general technique, which gave rise to the class equation, which we're it's not called the class equation here. So the class equation refers to the action by conjugation. But it's just this general idea of counting the size of a set by counting it according to the partition that you get on the set from the group action. So this action of Q on C will partition C. See, we already know how many things are in C. You know, there's n things in C. So this action partitions C. How big is a typical cell in this partition?
N-1. Although you count P as well.
Yeah, so I'm starting counting at 0. So starting indexing at 0. So the last one is n-1. So what's the partition? It's the partition of the set you're acting on by the orbits. Now, what's the size of your average typical orbit? We understand how it is that orbits get their sizes. Practicums, just trying to identify it here. It's there somewhere. I know what it is, I'm just looking for reference. Theorem 14.11, the orbit stabilizer. But I was hoping, your average orbit, curly O, one of these was curly O of a GIP, the size of an orbit. How did we get the size of an orbit? What did it relate it to? The index of a stabilizer. So we're using the action by Q here. So it's the index in Q. Is it colon or a comma they use? Colon. Size of an, so this is my scripto. Yeah, well, so that's your handwriting O for orbit. So the orbit's partition C. The orbit stabilizer theorem tells us the size of an orbit is an index. The index in the group doing the acting by the stabilizer of that element. And everything is finite groups here, so this is a simple quotient of the sizes of these groups. So tell me now, what kind of a number is this?
1 over GI. I don't know. I don't even know why how you made up that orbit GIP.
Well, so GIP is just a typical element here from the sets of left cosets.
Okay.
So I'm just referring to like any one of them, or just think of a typical one.
Okay.
This could be any one of them. It has a certain orbit.
Okay.
So this is all of GIP in the subscript position, because it was orbit of an element. And it's given by this quotient. So what kind of an integer? So this is an integer. It's a count of the size of an orbit. But what kind of an integer? In words, yeah. So it's some power of p, because Q, the size of Q is a power of p, and we're talking about a quotient of it. Now, did we say did we notate the size of Q? Yeah, we call Q p to the L. So let's say this is p to the. I need a number I haven't used yet. A letter I haven't used yet. P to the A. For some A. Now the A could be 0. We could be looking at a trivial orbit of size 1. but it's definitely less than or equal to L. Agreed? The Q is size P to the L. So the biggest A can be L. If the stabilizer was trivial, so the size of the stabilizer was 1, then this would have the full size P to the L.
What would be the size, what would the, what would be the size of the orbit?
Yeah, so potentially the orbit could have size, well, if A was 0, it would have size 1. Or it could have size P, P squared, P cubed, all the way up as far as P to the L. Because that's the size of Q. So that's the highest that this quotient can be. Now, remember, the size of C, which is equal to n, is the sum of the sizes of the orbits no, it's not. Sorry. So summing over the orbits, the size of each orbit. I'd be overcounting. So C, remember the picture, C, and it's partitioned by the orbits. Yeah? So just sum over the orbits, the size of the orbits. Now each orbit has size some power of P. Remember, P does not divide M. And that tells us something about at least one of these orbits. You see, if all of these orbits were as I've drawn them there, if they were all non-trivial, they all had size bigger than 1, that means they would all have to have size like a genuine power of P or P squared or P cubed. That means each orbit would have size divisible by P, which would imply M was divisible by P.
Why?
Well, because if this is divisible by P, this is divisible by P, they're all divisible by P, then the total count will be divisible by P.
Mm-hmm.
The total count is the sum over the sum of the counts of these cells. Okay. So if each orbit is non-trivial, size bigger than 1, the size of each orbit then is divisible by P, which implies P divides M. But we know P does not divide M. So if each orbit is non-trivial, i.e. size strictly bigger than 1, then P divides the size of each orbit. Every power of P is divisible by P except for this trivial power of P, P to the 0, which is 1. And hence, P divides M. But we know P does not divide M. That was the setup. M is the coprime part to P from the order. So that tells us that, so this little proof by contradiction tells us that there's at least one trivial orbit. So let's augment my picture here, stick in at least one little cell there which has one element. Could be multiple of them. It has to be at least one. Something to stop the total number being divisible by P. Therefore, there exists a trivial orbit. I.e., a special left coset. Well, it could be amongst a few special ones, but there's at least one. A special left coset. I'm going to drop the I, I'm just going to call it GP. Some G. The indexing was just important, and I just wanted to talk about how many of them there are. The sum left coset under the action by left multiplication by Q, its orbit just consists of itself. For every Q within Q, Q times G of P equals G of P. It never moves the left coset to a different one. Fixes it. This implies that on a setwise product level, we can say QG of P equals G of P. Remember the meaning of these expressions when we've got subgroups multiplying other subgroups? It stands for the set of all products. Choosing any element of Q, any element of P, or over all possible products that you can form like that. Well, that implies hit both sides with G inverse, and bracket, as we can by associativity. You get this. Now you're looking at a certain conjugate of Q. A certain conjugate of Q multiplying P gives you exactly P. Now from your theory of cosets before, this implies that this conjugate of Q is contained in or equal to P, just on a setwise level. On coset properties. And then, well, just for the purposes of getting the result we want, we just stick the conjugate on the P. So left and right multiply by G and G inverse. Now, this is a conjugate of P. P is a subgroup. It's a subgroup of this biggest possible size, P to the R. It's a P subgroup. Biggest possible one, according to its size, P to the R. What do we know? What's a conjugate of a subgroup is a? Subgroup. So, what's the size of the conjugate of the subgroup? Same as the size of the original. Yeah. Yeah. So this is again another P subgroup of order. Well, it's got the same order as P, which is P to the R. This biggest possible power of P within G. But now remember, the Q was special as well. The Q was one. God, it's 2 pages ago. The Q was a maximal P subgroup. A P subgroup that was not contained in any bigger one. It seems to be contained in a bigger one. What's the only way to resolve the two? They're the same. Yeah. If this was a strict inclusion, if that was a strictly smaller than this, then that would break the assumed property that Q was maximal. Because here it is contained in a somewhat bigger P subgroup. But Q, we said at the top, was assumed to not be contained in any bigger P subgroup. So the only way to resolve that with this set inclusion is if this is actually equality. Q is equal to this. So the size of Q is P to the R. So the size of Q at the beginning was P to the L, which we knew to be no bigger than R. But now the only way to resolve everything is if L is equal to R. Q was assumed to be maximal. I.e. contained in no bigger P subgroup. But we're looking at it contained in a potentially bigger one, so the only way to get out of that, to resolve all this if Q is equal to this. Okay. So therefore, as a consequence of that, i.e., or that certainly implies that the size of Q is equal to the size of this is equal to P to the R. Okay. So the second definition of Sylow P subgroup, the first definition of Sylow P subgroup implies the second. If you regard your Sylow P subgroups as being these maximal P subgroups, subgroups contained in the bigger P subgroups, they must have size P to the R, the biggest power of P. So it's a subtle point. So hence definition 1 implies definition 2. We already proved very easily that 2 implies 1. So they're equivalent. Now this does some of the work of the second. In fact, what we've seen there is really yeah, that constitutes a proof of the second Sylow theorem, I believe. Well, it's exciting because it kind of allows us to skip 2 lemmas. But now one of the lemmas we might need. Yeah, so I think what we've in a sense done with that argument, considering the action of a P subgroup on the cosets of another one, yeah, I believe I might have to double check this, but let's just look at the statement. So there are a couple of intervening lemmas, which we may need to code some of the lemmas for the third Sylow theorem. Yeah, I think we do, perhaps. So we might have to come back to those technical lemmas, but let's just look at the second Sylow. First Sylow theorem says you will find in G subgroups of size any power of P, or any power of P dividing the size of G. It's very assertive. There exist all these subgroups. The second Sylow theorem says, well, all the Sylow P, so there could be multiple loads of these P subgroups floating around within G, but there's a very strong systematic relationship between them. They're all conjugate to one another. Conjugacy, whether one set is a conjugate of another, is a equivalence relation. So this is saying there's only one equivalence class. So P1 and P2 are 2 Sylow P subgroups, so they're both of this maximum possible size, P to the R. Then you can find a G that will conjugate P1 and give you P2. Now, I believe he phrases the proof slightly differently, but it's again using an action. Well, the action by conjugacy of P1 on Q conjugacy classes of each PI. Yeah, so this is the action by Q conjugating on this set. Okay, which is what we've been doing. So if you look at this, argument we've just laid out here, right, which was for proving our equivalency between these two definitions, you can just rerun this argument. You only need to just change a few of the labels here. If at this stage here you let Q and P be 2 Sylow P subgroups. You know they both have the same size, P to the R. And then we can consider the action, say, all the left cosets of one of them, of the P, and consider the action of Q on C by left multiplication. We still know the size of C is M. It's partitioned by the orbits of this action Q. Each orbit must have size still, some power P. If all the orbits were non-trivial, it would imply P divided M. We know P does not divide M. Therefore, there's at least one trivial orbit. the orbit of coset GP for some G. And these calculations all go through here as well. Except you already know you must have equality here from the sizes. Okay, because now we know the equivalence of the definitions. We knew from the beginning that Q and P have the same size. So the only way to have a conjugate of Q being within P is if the conjugate of Q is equal to P. And vice versa. Q is a conjugate of P, P is a conjugate of Q. It's an equivalence relation. So from worrying a bit that we had to inject a load of extra work into the chapter, it actually turns out we can reuse it. Okay? So this argument also gives a proof. This argument also gives a proof of the second Sylow. All Sylow P subgroups are conjugate. Okay. A quick summary, second Sylow theorem. All the Sylow P subgroups are conjugate.
Okay.
Given any two of them, you can find an element little g that will conjugate one to give you the other. And the point I was making was the proof of it is exactly this argument that we just went through to prove that definition 1 implied definition 2. So I think the addition he needs in this chapter 15 there is just to straighten it out a little bit. The third Sylow theorem. Okay, I've only got a few minutes left, so let's just look at it in Luke. It's a double way of saying book. You say, well, Liverpool's close to one.
Oh, this is still done.
Shows your food there. Right. Let's look at the third Sylow theorem. Again, so it's just continually talking about this concept, the Sylow P subgroups. Second one said they're all conjugate. This third one, it doesn't quite tell you how many of them there are, but it gives you conditions on the count of the number. Two very useful conditions. So let G be a finite group, let P be a prime, dividing the order of G, yada yada. So there are Sylow P subgroups. They have size this biggest possible power of P that happens to divide order of G. Now, it doesn't give you a formula for the number of them, but it gives you two important pieces of information. The number of Sylow P subgroups, the number of different conjugates of one of them. Remember, they're all conjugate. The number of distinct subgroups is, it turns out, congruent to 1 modulo P, and in addition, a divisor of G. Some divisor of G. Yeah.
Isn't that making bad too? Is that expensive?
You live in Norway, I mean, what are you going to do?
Oh, yeah, okay, fair. Yeah, we did, didn't we?
Yeah.
It's the way it wasn't.
Yeah,
Oh, he is Norwegian. It's written right.
Now, okay, well, we'll read this proof together tomorrow, rather than trying to cram it into the final 2 minutes. But read it yourself in the meantime. Right? It just uses the same, very similar argument. Group action on a thing, count the number of cosets. Actually, it does go back to one of the lemmas, so we might need to go back and quietly prove lemma 15.6. Okay. So we'll do that tomorrow, and then we'll start looking at applications. Those two, that third theorem, these kind of number theory conditions on the count, the number of subgroups, you can make that work a lot for you. And draw a lot of, in certain instances, draw a lot of conclusions from that. Okay, good work. I shall see you tomorrow for this.